The energy absorbed from a photon of light can also be used to promote addition reactions, and in this webcast we'll see two examples. In the first case, the carbonyl will serve as the chromophore and will add the elements of carbon and hydrogen across the carbon-oxygen double bond. It's an intramolecular reaction, and the result will be a new carbon-carbon bond as well as a hydrogen-oxygen bond. The mechanism of this reaction begins with an N to pi star transition of the carbonyl group. That photoexcitation process pushes an electron from the non-bonding level into pi star, leaving the non-bonding level half empty, making it very electrophilic. The nucleophilic species will be the pair of electrons in the sigma orbital of the carbon-hydrogen bond. The key frontier orbital interactions, then, would be a sigma to HOMO* donation, where HOMO* is the non-bonding level, now half empty. This three-dimensional model will better show the molecular orbitals that are involved. Let's turn on that non-bonding orbital and that sigma orbital and zoom in. If we take a look from the side, we'll be able to clearly see that that filled sigma orbital can interact with that partially empty non-bonded orbital on oxygen, transferring that hydrogen over to the oxygen. Here's how we can represent the process with curved arrows. We'll represent the excited state as this diradical species that will interact with the carbon-hydrogen bond. A new bond will be obtained between the oxygen atom and the hydrogen. It's shown here. That leaves behind a carbon-centered radical there, and we also have, from our excited state, a second carbon-centered radical there. And so the final step simply involves combining those two radicals to make the new carbon-carbon bond in the second step of the process. In this second photo addition, we'll add the elements of XH across the carbon-carbon double bond. That'll be the chromophore. The specific example we'll look at is this cyclohexene, which adds the elements of OH from methanol across that carbon-carbon double bond. It generates a new oxygen-carbon bond along with a new carbon-hydrogen bond. Here's a mechanism that explains the process. Photoexcitation of this species is a pi to pi star transition, so we're jacking an electron from pi up into pi star, making pi star very nucleophilic. If we look at the Schmoe calculation of what pi star looks like, we see that the greatest orbital coefficient is on that alkene. That would generate a structure that we could represent here as this spheroionic species in which the lone pair is positioned on that alkene that Schmoe said had the greatest electron density. Let's use that as our nucleophile, and so that the key frontier molecular orbital interaction is going to be a LUMO*, in other words, pi star, LUMO* sigma star interaction, where sigma star is the sigma star orbital of this oxygen-hydrogen bond. And so the curved arrows for this process will look something like this. We'll take that pair of electrons on carbon, add it into sigma star, and make the alkoxide anion. That'll leave behind this carbocation. The carbocation is then captured in an A sub n step to generate the final product.